the moderator for the Ferg weekly discussion. And right now we have a very incredible speaker, Mr. Joe Honggeun. How are you doing, Mr. Joe Honggeun?
I'm doing good. Thanks.
Okay, before we get started, there will be an opening speech from Mr. Mizam as leader of IAGI, Jawa Barat, Banten. Mr. Mizam, time is yours.
Thank you, the moderator. Good evening, everyone. Good evening, Honggeun. My name is Mirzam actually I'm lecturer from ITB, Bangladesh Institute and Technology, and also the head of Indonesian Geologists Association for West Java and Banten. Welcome to our weekly discussion from Ferg Geoscience Indonesia and Indonesia Geologists Association. And as mentioned by the moderator, that tonight we have special guest speaker from INHA University, South Korea, Dr. Honggeun. He will deliver about generative adversarial networks for static and dynamic data integration in subsurface modeling. Dr. Honggeun, on behalf of Ferg Geoscience Indonesia and Indonesian Geologists Association, I would like to say thank you for your time for sharing your knowledge. I believe that tonight we can learn something new about the static and dynamic data integration, especially in subsurface modeling. And I hope this is will be the starting point for us to have collaboration between INHA University and many universities in Indonesia. I think that's all from me, and please enjoy the show. Thank you, Faras, and thank you, Dr. Honggeun.
Okay, thank you very much, Mr. Mizam, for the opening speech. And before we get started, I would like to share about our profile speaker for tonight. Here's Mr. Joe Honggeun Sonsengnim, an assistant professor from INHA University, and he pursued his PhD in University of Texas at Austin, under in Faculty of Petroleum and Geoscience Engineering, and graduated at 2021. And for the professional experience, we can see he has a lot of experience from in the industry with BP, and currently he's working as assistant professor with interest topic machine learning, if I'm not mistaken, and also role-based reservoir modeling. And today he will speak about the structural geologies. And for the publication, he has written a lot of journal and paper, over 30 publications, if I'm mistaken, and already has been cited over 400 times. And okay, without further ado, for the next 45 minutes, we will listen to what Mr. Joe Honggeun Songsenim has been working on, and there will be a lot of things that we could acquire from his presentation. And after he presented, will be continued with Q&A questions. You may raise your hand if you have a question, or you may write in the chat column. Okay, go ahead, Mr. Joe Honggeun. Time is yours.
Thank you so much, Faras. Thank you so much for your generous introduction. And it's my great honor to this opportunity to share my research work at FERG Weekly Discussion Forum. So let me share my screen really quick. So can everyone see my screen?
Yes.
Yep.
Okay, great. My name is Honggeun, and I'm now serving as an assistant professor at INHA University in South Korea, and I did a PhD at University of Texas at Austin, and under the advisory of Dr. Michael Pott and Dr. Junira. We had a same class back in 2018 and 2019, and that's how I had this great opportunity to give a talk on this opportunity. And today I'm going to talk about generative adversarial network for static and dynamic data integration and subsurface modeling. Generative adversarial network is one type of the machine learning techniques. And in this talk, I will initiate with motivations. So what's the problems in the typical or the most subsurface modeling method, and why we need a deep learning or the generative adversarial network as an alternative. And by using that, what are the benefits that we can expect? That's going to be the end. And because I haven't, because the deep learning applications in the subsurface modeling, as I know, it's an ongoing process and ongoing researches. So there's more things that we can potentially do in this work domain. And maybe in the last couple of slides, I will briefly introduce you some future opportunity that we can be working on using the deep learning in the subsurface modeling. This is a little bit of myself, and this photo, I took this photo on the last day at BP, and after this, this was like a Friday afternoon, and right after this, I went to the airport right away, and over the weekend, I mean the right next Monday, I had a very first class at INHA University, so that's how this photo is quite meaningful for me. And also, before pursuing my PhD, I also had a chance to work for the Korea Gas Corporation. And in this company, I've been participating in, I had participated in the Indonesian LNG gas development project. As far as I remember, the project was called the Senro Truly LNG development project. And Pertamina was the main company that we been working together. And my research interests include the subsurface data analytics or modelings and some simulation. And recently, I've been focused on the CCS, carbon storage. Let me get started with my executive summary, because these three messages are the one that I wish to share with you today. First, now we have more advanced subsurface modeling method that is called the rule-based modeling method. So using this rule-based modeling method, we now be able to integrate geological concepts or the rules to the subsurface model in more direct way. However, due to the high stochasticity in the geological nature, integrating the quantitative information such as the well log, seismic, or production history is a remaining obstacles to the broader application of this rule-based modeling method. That's why we still mostly rely on the 2-point statistics or multi-point statistics, like Kriging or SGS or SIS. So to tackle these limitations, we propose the machine learning associated or machine learning assisted reservoir modeling method. And this is mainly to enable data conditioning while preserving the geological realism in our subsurface model. And as an example, I will provide you the generative adversarial network. And this show that it performed a good, effective dimensionality reductions. And also, it enables us to integrate some of the static and the dynamic data in our model. And here are the agenda. First, I will start with a motivation, and then I will explain what the generative adversarial network is. And then I will continue to the 3 different examples. First 2 examples are related to the static data. First is well log, and the second one is seismic data. And then lastly, dynamic data integration. In other words, history matching, how we can do the history matching with assistance of GAN. And I will briefly introduce you some possible potential future work. and I will conclude with some key takeaways. So my PhD work is mainly motivated on submarine turbidite fan. So submarine turbidite fan is one of the depositional environment that is commonly observed in the Gulf of Mexico. The Gulf of Mexico itself is a passive continental margins. And we know that after 1980, we've been found a lot of the oil and gas in such a particular environment. So that's how it has been a quite crucial place and prospect. And as we study more in the submarine turbidite fan, in a more recent study, we found that they have a unique hierarchical architectures that makes the internal structure of the submarine turbidite very unique. Here we have some example. On the left-hand side, we have a block diagram of the submarine turbidite fan. From the continental slope, we have a basin flow, and as the turbidite flowing down to the flow, they start to deposit on top of the basin flow. And as they deposit, they have a very unique hierarchical structures. And on the right-hand side, we have detailed view of that hierarchical structures. So one big lobe complex, it may has 40 kilometer by 30 kilometer by 50 meter dimensions. And the one complex may have several lobes. And also each lobe may have several lobe element. So, and individual hierarchies have their unique structure, and this is very important. However, the details of this lobe element is subseismic resolution, so we cannot reveal entire details from the seismic survey. And this heterogeneity and also as we are exploring in the deep water, the number of varies very, very limited. High heterogeneity and the sparse weather data often lead to high degree of uncertainty in the deep water exploration in the Gulf of Mexico. So that's how I start to working on the submarine fan. And as one way to alleviate this issue, rule-based modeling method was proposed by Dr. Perch in 2005. And the rule-based modeling method, we basically simulate the sediment dynamics to generate a numeric description of the reservoir architectures. And by doing that, we can have more realistic the boundaries of the lobe element. And if we follow that boundaries, and if we assign or allocate the porosity and the permeability, the properties that we are interested based on that architecture, then we can make more realistic subsurface model. So here we have two different examples. On the left-hand side, this is from Perch and Deutsch. This is cross-sectional view of deep water submarine fan, and we can see the individual lobes, lobe elements boundary, and the porosity are assigned following the boundary. And on the right-hand side, we have a 3D view of this rule-based model for the deep water submarine fan. In more recent work, this rule-based modeling method has been referred as various names, such as surface-based, event-based, hybrid, or process-oriented, or rule-based modeling method. But in this presentation, I will just use the word the rule-based modeling method. Here is one example of the rule-based modeling method that we implement in this study. It takes three major geological input parameters. The first parameter is related to the geometry of the element. Because we are now working on this lobe, we are assuming the ellipsoidal lobate element, and the geometry can be determined by its width, length, and thickness. And we have three different examples. So the first one is isotropic lobe, and the second and third one is more like anisotropic with a different aspect ratio. And once we have the geometry of the slope element, then the next key parameters is related to the stacking pattern. This lobe element can be stacked either by random stacking or the perfect compensation stacking. And in the nature, we actually observed the different stacking pattern in the different locations. For example, in the high energy environment, the deposit is likely to be deposited regardless of the current topography. That's how we more observe the random stacking pattern. But in the low energy environment, such as the proximal area of the no, actually the distal area of the submarine fan, once the deposit or the turbidite go down to the fan, then they lose all the energy. So now this deposit specifically found the lowest locations, and then they deposit in that location. So in that case, we were more likely to observe the compensation stacking. And by Straub, this tendency can be measured as a compensation index. This is a metric. And we also found that we can control this index by controlling one of the input parameters in our rule-based modeling method, and record this as a compositional exponent. If the compositional exponent is a 0, then it will follow random stacking. And if it's larger than 5, then it will follow the perfect compensation stacking. And any number between 0 and 5, it will follow a intermediate stacking pattern. And once we have the structure, then now we have to consider how to allocate the rock properties, like petrophysical properties such as the porosity and the permeability. And for this particular work, we implement hierarchical trend modeling method from Ferg in 2004. So after we provided the structures, then we can use the relative location of the individual graded blocks, and using that relative location, we can assign the different trend. For example, we can provide a coarsening up trend in the entire scale, but we can also provide a finding up trend in the element scale. So finding up means we expect a high permeability or high porous rock in the middle of the lobe element, whereas in the boundary we are likely to have a more shaly or the fine sample. So here is the workflow. First, we have to define the initial bathymetry, extent of the reservoir, and the geometry, and then we are gonna iterate this part. So first, we need to compute the probability map of the next deposit location, and we run the simulation to determine the next deposit. And once we determine the next deposit, then we need to update the bathymetry. And we do this iteratively until we filled up entire extent of the reservoir. And once we finish this blue part, the result will be are shown on the right-hand side in the blue box here. So here we have the structural surfaces of individual lobe element in 3D view and in cross-section view. And this black line indicate the individual boundaries between the lobes. And then lastly, by applying the hierarchical trend model, based on this structure, we can assign the permeability and porosity. In this example, we are visualizing the permeability. So following the lobe element, in the middle of the lobe, we are expecting the higher permeability. And then in the boundary, we are having the low permeability due to the shale drape that is most commonly observed. And also, if we compare the upper lobe element and then the lower lobe element, even though they are the same in the middle, upper lobe are likely to have a higher permeability than the lower lobe, and that's due to the compaction. And this can be adjusted depending on our geological assumption or the observation. So here we have one example of the rule-based modeling method for submarine fan. And these three geological input parameters are important not only for the aesthetic pleasuring for the modeling process, but also for the prediction for future performance. So here we perform the sensitivity analysis. Here we had one injector in the middle and the 4 producers in each side. So this is the inverted 5-spot pattern. And we perform the statistical hypothesis test, whether the influence of each changes are significantly influential to the recovery factor or not. So for example, the stacking pattern, sticking pattern wasn't very important in the early or middle stage, but in the later stage, sticking pattern is likely to impact the recovery factor and the geometry all across the production stages. The geometry has been influencing the recovery factor as well. Globally, the larger element, the lower recovery factor is expected. And also heterogeneity, this comes from the hierarchical trend that we used in the last step. So, and also we have a different impact on the recovery factor. So this indicates that quantifying these three geological parameters is very crucial to improve the future predictions in the real development project. However, this rule-based modeling method is not used as a main tool in geostatistics, and that's because it has a very crucial limitations. That is, conditioning a rule-based modeling to the subsurface data has been remained as obstacles for the broader applications, such as the well log, seismic, and the production history. This is my favorite plot. Here we are comparing the several different subsurface modeling method. So each black point indicate different method, and the x-axis indicate the different ability. So if the x-axis on the left, it indicate the ability to condition to the common data type. So how easy or straightforward they are to condition to the given data. And on the right-hand side, we have another ability that is how better they reproduce the realistic features in their model. Variogram-based or multi-points-based or object-based modeling method, which we often call the conventional geostatistical method, they are belong to the left-hand side. We didn't have or experience much difficulty in the conditioning data. However, the rule-based modeling method, we are integrating more geological concepts such as stacking and filling, forward model, topographic update, flow paths, and so on. So as we are having more geological concepts in our subsurface model, and then as we can now make more realistic subsurface model, now we are losing the capability of the conditioning the data because now it moves to the right-hand side. The rule-based modeling method belong to this gray area. And so this is the big limitations to broaden the application of the rule-based modeling method as a standard. Here we have one example. Let's say we had one good rule-based modeling method model, and here we have well logs. In the typical geostatistics, we are populating the property from the well log. So we assign this property and then we populate the rest of the background. However, in the rule-based modeling method, as we are following the more like geological sequence, and that geological sequence is very stochastic, there's no such way for us to directly condition this well log data into the rule-based model. So that's big limitation. And that's how in this presentation, I will explain how we can use one of the machine learning algorithm that is GAN, or Generative Adversarial Network. So here we have a rule-based model, and to broaden their applications, now we are going to apply the two different type of the GAN. The first one is this is the initial type of the GAN, and then the second type, in case we have additional information that we can use, we can also use the conditioner GAN. So the first one is not unconditional GAN, which is the first type of GAN, and the second one is unconditional GAN that we can implement in case we have some additional information about the subsurface. So by using the unconditional GAN and conditional GAN, I will provide you how we can well log integration, and also how we can potentially use the seismic information into our subsurface model. And then lastly, by using the unconditional GAN, I also briefly introduce how we can do the dynamic data integration in this rule-based modeling method. As I said, as a the algorithm, we are implementing the generative adversarial network. And this generative adversarial network, or GAN in short, first proposed by the Ian Goodfellow in 2014. And here we have a schematic diagram of the GAN, how the GAN works. So we are saving our generated models in the training data sets. And then we are building the two different neural nets. The first neural net is called the generator, and the second neural net is called the discriminator. And typically, as we are now dealing with a 3D geological model that is the voxelized images, we often use the convolution neural net for the generator and the discriminator. They have two different roles. The generator, first of all, generator, it takes a random latent vectors, which are simply random values that are drawn from a standard Gaussian distribution, whose mean is 0 and the standard deviation is 1. So it takes some random noise, and then it converts that random noise to the sample that we are interested of. It can be human face, cat face, dog face. In our particular example, we want to generate the rule-based models. Here we have a 3D channelized reservoir example. So that means we are expecting this generator to generate a 3D channelized reservoir. And this discriminator, whereas, takes the sample either from our training data set or from the generator. And then it's a basically classifier. It classifies whether the input image is real or not. If the sample is from our training data set, which we have are the geological features, then discriminator are supposed to tell, oh, it's real. So it will return like a 1. 1 means real, like a true. And if it's from the generator, then it's a fake. So that it's supposed to predict like a 0. 0 means false. Basically, discriminator is trained to more sophisticated to tell whether it's real or not. And the generator is trained to more sophisticated for the discriminator. So they are trained in a very competitional way, and that's why it's called the adversarial network, because they are competing each other. Their competitions is mathematically described as a given loss function. So it's using the same loss function, but the discriminator want to maximize it, whereas the generator want to minimize it. So it's a minimax game. My favorite analogy of the GAN is competition between the forger and the detectives. The forger, it may want to create more realistic, for example, money that is fake, and then the detective are supposed to tell whether the money is real or not in a more sophisticated way. In the very beginning, the generator, it doesn't really have any information about our rule-based model, so it will simply generate a random noise, and that allows the detective easily tell whether it's real or not, because a real one, it has some unique geometric features, whereas the initial output from the generator, it's simply noise, so it's really easy to tell. However, based on the feedback from the here, now in the second iteration, the generator now figure out in which way they can make more realistic money, or more realistic rule-based model. So in the second attempt, they will have more realistic feature than the previous steps, and in this way, discriminator may fooled. But however, based on the feedback, now this time the discriminator will be reinforced, and now the generator are supposed to generate a more realistic model than the previous iteration. Otherwise, it will be easily told by the discriminator. So in such way, discriminator will be sophisticated, at the same time, generator also have a chance to be trained. Here we have a more detailed structure. So as I said, it's a convolution neural net. Generator start from a random latent vectors, which is some simple numeric array, and then it expand to a feature map, and the feature map expand as it continue, and then in the end we will have the same size as our subsurface model. And discriminator, it takes the model itself. So it starts from the big feature map and then squeeze it, and then in the end we will have just one numeric value that tells whether it's real or not. If it's real, then it will be labeled as a 1, otherwise it is labeled as a 0. Here we have one brief example. This is called egg model, whose dimension is 60 by 60 by 7. It's a 3D channelized reservoir, and and also we can also have 100 realizations of this egg model. So they have this channel, fluvial channel features in the subsurface layer. So and by using this 100, the provided 100 realizations, we trained again, and then we ask again to generate the new examples that we have here. So here we have 2 different comparison. After we trained, on the left-hand side, we have 25 realizations in the training data set. And on the right-hand side, we have the new 25 examples from the trained again, or from the trained generator. Individual newly generated models have a important geological feature that is continuity in the channel. So the channels always continued from the north to the south, and also they also have enough sinuosity that resemble our provided training data set. And here we have better animations. So the generator takes the random latent vector, and that random latent vector consists of 100 numeric value. And now we are changing that numeric value continuously. And on the right-hand side, we are having the corresponding outcomes. So as we are updating or changing the latent noise continuously, we can also expect the continuous response in the subsurface model or in the realizations. And here we have a very unique benefit. That means if we want to change our models while preserving the geological features, we can simply change the latent vectors. And this generator will always assure the geological features that we had in our initial assumptions. So we can continuously change our subsurface model. At the same time, we can expect the key geometric features are preserved. If we go back to the rule-based model, we can also train again for this rule-based modeling method. So in the beginning, it just simply generates a random noise, but as we continue, then in the final step, generators start to create a very similar subsurface model as our training data set. And here we have more detailed comparison. So we had 100 realization from the GAN that are colored by this red point or red cluster, and the rule-based modeling method rule-based models, they are colored by the blue. And by using the multi-dimensional scaling, we can project it to the 2D dimensional space so that we can easily compare it. So if they are similar to each other, then we are expecting no significant difference between the red cluster and the blue cluster. That's the goal. So in the beginning, this red cluster is far from the blue cluster. That's what expected. And then as we continue, then the models start to build a loft. It's very loft because it's not very detailed, but it start to make or mimic the boundary between the lobes. And as we continue more, then now it more focus on the details. And now the two clusters meet each other. And then after 40,000 epochs, the training process, now the two clusters are mixed together, and now it become indistinguishable. So in this way, we can tell or we can verify that our trained again now continuously generate the rule-based models that has the similar features as we expected. From the GAN, now we want to condition to the well-log data. So to condition the well-log data, we need one more step to implement, and that is a semantic imaging painting. image in painting is the algorithm to restore any corrupted part of the images. And this semantic image in painting takes two different concepts. First one is the contextual, and the second one is perceptual. So simply speaking, contextual means the restored part should be harmonically generated based on the background, and the perceptual means the generated image itself should be realistic enough. So this conceptual and the perceptual losses are combined together, and this lambda is hyperparameter to determine the balance between these two. And by minimizing this semantic loss, we can generate a realistic restoration of the images. Here we have one example. We had one empty and void mark, and after semantic image in painting, it generates something like this. And here we also generate it like this in human face, in car, and so on. Even though the image in painting is not necessary to replicate our original data set, because that's not our purpose. The purpose is, if we hide a human's nose or eyes, then we are expecting the eyes and nose are restored, right? And as long as the restored part is under the context of the provided images which are input, then this is we call this successful. We can consider this successful. So by using the semantic image in painting, first we generate the multiple rule-based models, and we extract the geological features from training the GAN. And when we implement it, we generate the one rule-based model and then put the empty void near the well logs. And in the center of each void, we are assigning the well logs information. And by using GAN and semantic image in painting, we can fill up this empty void so that we can generate a complete model that are preserving the well logs, and at the same time make some harmony with the background rule-based models. Here we have a more detailed example. We have a background rule-based model, and the green means we are assigning the well logs, and then the blue means the void. So we do not have any information yet. And from here, we are applying the semantic image in painting to restore the black colored area here. And here we have one example. This 3D view and 2D cross-sectional view, vertically and horizontally. If you look at the horizontal view, we've been expecting this circular lobe boundary, and we can observe that the restored part is harmonically generate the boundaries and under the context of this rule-based model. And also in the vertical view, we can see how the boundary of the lobe are successfully restored. So this is the one applications that we implement. And by using the GAN and semantic image in painting, we demonstrate that we can potentially solve the hard data conditioning problem in the rule-based modeling method. And here we have a second type of the GAN. Previously, the generator only takes the latent random vector, which is random noise. However, in case we have some additional information, such as a stratigraphic profile, so if we know the boundary, or if we can provide some hint about how the lobe elements boundary are look like, then we can use that information as an additional information to the generator, so that we can generate the sample that follows the lobe boundary that we provided from the left-hand side. This is first suggested by the ISOLA in 2018, and this method is called the image-to-image translation, or conditional GAN, or more oftenly, people sometimes call it like a pix-to-pix, like a pixel-to-pixel translation. And here, on top of the latent random vector that is a Z, we also have additional observed information that is labeled as a X. And here we have the loss function of the training process. The first term is the same as what we had earlier, the GAN loss. And basically, the GAN loss is designed to be realistic. So we want to get the sample that mimic the key features that we had in our training data set. But in the second term is more for our new observation. We want to have less misfit between our additional information and our outcomes. So that's the second term of the conditional against loss. Here we have one brief example. Here we have a ground truth, and here we provide a stratigraphic profile in 3D view and cross-sectional view. And once we successfully train this conditioner again, we can predict the 3D subsurface model on the right-hand side. And as you can see here, individual lobes follows the boundary that we provided from the left-hand side that are given here. This is one of our training data sets, so there's no benefit of doing this. But however, once we properly train the conditioner again, then we can potentially provide a more interesting geological feature, such as the structural changes. Here we have two different examples. In case we have a fault, or in case we have an uplift. And of course, fault and uplift, these are the common observation in deepwater rock reservoir due to the existence of the salt dome in the more deeper formation. We observe a lot uplift or the fault. So in case we can assume the fault or the uplift in our submarine rock fan, and if we provided the information by providing the structural changes in the boundary, then we can also use that conditioner again to generate or predict the porosity on the right hand side. And as you can see, especially for the fault, we can see how the boundaries are connected from the different across the fault, because this part was here and this part was here and this part was, I believe, here. So we can see how they are consistently populated. And I believe this feature potentially can be used for a seismic data integration, because from the seismic we can expect some of the stratigraphy profiles, and if you have, then we can use that to properly train the conditioner again, so that we can get the output in the end. And then lastly, it's about the dynamic data integration or history matching. And here we have one of the most commonly used history matching algorithm, that is ensemble Kalman filter. If you know ESMDA, I think ESMDA is more widely used than ensemble Kalman filter itself. Ensemble Kalman filter or ensemble smoother or ensemble smoother multi-data assimilation, they are the family. So they are slightly different, but they are using the same concept in the deep side of the algorithm. So here I explain how briefly, I will briefly explain you how the ensemble Kalman filter works. So instead of dealing with just one or two subsystem model, now we are dealing with multiple realizations. And the multiple realization is sometimes called the ensemble. And Y1, Y2, and Yn, they are indicated individual subsurface models. So we have, for example, 100 different subsurface models, and they are represented by the Y1, Y2, and Yn. And individual Y consists of the static parameters and dynamic parameters. Static parameters such as the porosity and the permeability, and the dynamic parameters such as the production estimate from the wells. So this is how, and this individual Y is called a state vector, and this capital Y is just a state matrix because it contained the ensemble. And here we have two different steps in the ensemble Kalman filter. So first step is the prediction. By using this simulator, we predict our next time steps outcomes, and of course that outcomes is not perfectly fit to our observation. So and that means we need to assimilate. So we need to update our ensemble based on the misfit between our observation and our estimation. And this is how we update. This YP means prior and YA means assimilated or updated ensemble. And the prior ensemble is updated by the Kalman gain weighted misfit. So the DOBS means observation, and this is our estimation from the individual subsurface model. So this is misfit, and that misfit is multiplied by the Kalman gain, and the Kalman gain statistically derived as follow. And the detailed are can be found any ensemble Kalman filter manuscript, the papers, and because there's a lot of papers about the ensemble Kalman filter. I think this is the only slide that I have about the ensemble Kalman filter. And here we have a workflow how the typical ensemble Kalman filter can be applied to the subsurface model. So first we generate the ensemble, an individual ensemble. In our case, as we are now having the different boundaries, we are expecting this bimodal distribution of the permeability. We have some shaly rock and there's a sand rock. And we run the simulator so that we can get the WOPR, where oil production rate, and this is how we can build a prior state vector, and we calculate the Kalman gain, we update it, and then we continue this until we use up our other observation, and then in the end we run the future prediction based on the final updated ensemble. Here we have one crucial limit problem, that is, in the ensemble Kalman filter we are expecting the Gaussian distribution of the parameters. However, as you can see here, this probability is not Gaussian. So we have this bimodal distribution, and if we just directly use the ensemble Kalman filter, then that means this bimodal distribution may damage it in the end, and that means we may not have a clear boundary between the lobes. And that's how we expanded to combining the GAN with the ensemble Kalman filter. And here, key difference is instead of updating the permeability directly, now we are updating the latent random vectors, the input for individual surface models. So this Z, the latent random vector, as I said, in the training process, we assume they follow the standard Gaussian distribution, which is perfectly fit to the Gaussian assumption in the ensemble Kalman filter. And even though we run the ensemble Kalman filter over and over again, this state random vector will be just Gaussian as they are, and also every time they pass through the generator, we can always restore that bimodal distribution in the end. Here we have a one reference case, and here we have final outcome. So in this example, we predict up to 2,500 days, and we are basically use the 500 days of the history as a history data. And with a GAN assist ensemble Kalman filter, we can preserve the clear boundary of the lobe as well as the bimodal distribution. So in this way, we can preserve more geological feature. Whereas if we just use the typical ensemble Kalman filter, as I said, the final outcomes will be the unimodal distribution, and that will basically break every geological realism. That means even though we had a lot of effort of building the rule-based modeling method to integrate more geological realism in it, with a typical standard Gaussian ensemble Kalman filter, we cannot preserve it in the end. So there's no effort. I mean, the effort is not useful in the end. And that geological realism also crucially impact on the production, future production accuracy. So light gray are the initial ensemble, and then the dark blue, the black lines are the updated ensemble's outcomes, and the red is ground truth. And please note that we use the production data up to the 500 days. So from the GAN assist ensemble Kalman filter, the black lines that cover the ground truth, that means we are adequately predict the future prediction, whereas on the right hand side they are too narrow, and they have a significant misfit between the ground truth and the final outcome. So this also verify how important it is to integrate the GAN into the ensemble Kalman filter as well. And from now on, this is about the future opportunity. The GAN, it takes more than 1,000 or the tens of thousands training realizations, and that may be too expensive because we may not have enough realization of a subsurface model to train the GAN. And the more complex geological feature we have in our GAN, and the more training data set we may need. As an alternative here, people start to working on how can we generate the multiple realizations from just one single images. Here we have one example, and then the secret is, by the way, this is from the Shahem, and she developed this workflow in 2019. And then the secret is, instead of starting from the high resolution or the original resolution of the image, we upscaled it, and then from the upscaled more realization, because it's too simple, that we may be able to train the GAN with the one realizations, and we continue to the next scale and the next scale and so on. So we tackled from the simple problem, and then we move on to the complicated problem in the end. And in this way, she were able to perform this generating the multiple realization from the one single images. And here we have a more detailed example. So we are basically changing the random noise, and that random noise are propagate to the top so that we can get the multiple realizations. And of course, we can implement it to the our subsurface domain. Left-hand side, we have one fluvial channel, and on the right-hand side, we have a delta system. From the one realizations, we can generate the 25 different outcomes on the right-hand side. And here are key takeaways. Realistic geological input parameters are prerequisite, not only for honoring the geological observation, but also for the reliable production prediction. And that's how the rule-based modeling methods are proposed. And GAN can successfully extract the main geological features of the rule-based model. And that enables generating a realistic heterogeneity and the continuity in our new realizations. And semantic imaging painting and conditioner GAN, we were able to do the direct static data conditioning, and also by combining the GAN with the ensemble common filter, we can also improve the performance. And then lastly, the flexibility of the machine learning. So we only provide example for the fluvial channels or submarine fan, but this workflow can easily expand it to any type of the geological depositional environment, because the machine learning itself doesn't really have any limitations. So as long as we have enough training data set and enough domain knowledge, then we can always tweak the provided machine learning model to solve our problem in our side. And this is our I prepared for today, and thank you for listening.
Okay, thank you very much. Participant, please give applause for Mr. Jo Honggeun for the presentations. Personally, I'm truly impressed with the coding process. It seems so complicated, and yeah, I'm stunned with the work you have done. And now we continue to the Q&A question and answer sessions for the participant who may have a question. Please raise your hand, or you may write out in the chat column. We have one question from Asido, but he wrote in Bahasa, so I have to translate. How you acquire the data set? Is it a synthetic data set or real data that has been processed and then collected? And second one is the library or the implementation library, what you use, and is there any GitHub open public that can be accessed?
Okay, sure. Thank you for the question. First of all, the given example or our training data set, and for this particular one, I've done this work during my PhD. So, and the rule-based models, they are referred to the geological papers. So, for example, the dimensions and then the stacking pattern, we followed what we observed from the geological papers, but the data set itself, they are synthetically populated information. However, after I joined the BP, in the BP, we had a more assets that we've been working on, and the people start to in the year when I joined the BP, that's the year people start to seeking for the chance of using the deep learning or the machine learning to tackle their real problem. And there we had some opportunity to expand my workflow to implement it in the real data set. And there we had some example and there was some meaningful outcomes. But of course, after I left my BP, I cannot access the other outcomes here. So in this presentation, the other data sets or the examples are the synthetic at the moment. And also for the package in the library, I mainly use the Python TensorFlow. TensorFlow is the package to build any type of neural net, and again, of course, it's also neural net. And I know that people now openly use the PyTorch than the TensorFlow, because I think that's the trend. People start to, I think already most of the newly published paper, they only provided that the finer examples only in the PyTorch, not in the TensorFlow. So if you are the new runner for the neural net, I highly recommend to run the PyTorch than the TensorFlow. People says it's more straightforward, but for me, I'm still mainly rely on the TensorFlow. And for the example library, I actually have some GitHub repository that I can provide. So the only challenges that we may have in using the GAN or any type of machine learning into the subsurface is that the typical examples in the computer vision community, they only deal with the 2D images, like a human face, cat face, they are 2D, whereas in our subsurface domain, we are now looking at the 3D. It should be 3D, not in 2D images. So other provided information or the provided the workflow, they are mainly developed for the 2D images, but you may need to learn the convolutional neural net or some structure of the neural net so that you can expand it to the 3D. So, but that's not a big deal actually. Once you can use it, it's really easy to do so. Maybe after this presentation, I can share the GitHub repository that you can try, and actually in that repository you can get the access for the like a 3D channelized reservoir, the egg model example that we had here. Wait a second. I can provide you some demo to make this work, like a 3D channelized reservoir, 100 training data sets, and generate the GAN, and then populate the new realizations from the GAN.
Okay, thank you very much for the answer, Mr. Joe. Is there okay? Thumbs up from Asido means his answer very well. Okay, we continue to next question from Adi Junira. Thank you for your great presentation, Honggeun. I have few questions. First one, you mentioned that ensemble Kalman filter is the most commonly used for algorithm for assisted history matching. Would you please comment on how is it compared with Markov chain Monte Carlo or MCMC? If my memory serves me well, in Dr. Sevamori's group, the commonly used algorithm for ARM is MCMC. Why some use ensemble Kalman filter while some other use MCMC? And second, okay, may I continue to the full question? Okay. Afterwards, you may answer. Second one, you mentioned the limitation of generative adversarial for application in subsurface modeling. Could you please elaborate more on that? And third one, you mentioned that machine learning or your presentation subject is an ongoing research. Could you comment when this approach or method would be adopted by industry, or is it already adopted? And last one, for I noticed some people in the industry have reservation for adopting new technique. They argued, why use something that I am not familiar with if the result at the end of the day would be just the same? with the method I'm using now. Could you please comment on that? There are many questions. Thank you very much for the Junira. And yeah, you may answer, Mr. Jo Honggeun.
Okay, thank you for the question, Dr. Chunira. And for the first question, I think the MCMC is a very popularly used history matching algorithm. And I think MCMC and the ensemble common filter, or the ensemble-based history matching algorithm, they have a unique advantage and a disadvantage, I think. One thing that people may concern in doing the history matching is that they don't want to converge the answer too early. Sometimes we over certain about the production history. So let's say if we have a 20 years of the production history, that production history may not be enough to deterministically determine the details of our subsurface domain. However, because of most of the history matching algorithm, it's mainly designed to minimize the misfit between our observation and the misfit, and it sometimes seems like our final outcomes follow the earlier production history, and we are so sure about this answer. But if you think about the inverse problems nature, that the uniqueness of solution is never guaranteed. So that's how people sometimes need a more diversity than the accuracy. We do not want to over certainty, and in that perspective, I believe because ensemble common filter in the end it will provide a range of like a broad range of the prediction rather than a one good answer in the end. It's better in that perspective, but the ensemble common filter, that means we need to run the ensemble, and that running the multiple ensemble means it takes a lot of the simulation time. So without the cluster or high performance computer or the multiple parallel processing, we may not be able. I mean, not every computational resources may not be ready for this heavy computational expense. So in that way, in that sense, probably the ensemble computer is not very attractive, but I think that's pros and cons. I still believe that a lot of researchers and then a lot of the people from the industry, they are still using the MCMC a lot. And the second question, the limitations. The limitation is if we have more complex geological features or some geometrical attribute, then that means we need a more training data set to let the generator fully understand what's really going on. If it's just a simple image, then maybe we just need 10 or 100 images. But if it's really high resolution or the high detailed and maybe some art from some famous painter, then that means we may want to have the generator, the GAN itself, need a more training data set than we have. That means without the given enough number of the training data sets, then the generator may not be readily available. First obstacles of implementing the GAN in the real asset was in the most of the case, in particular industry, they may not have that multiple realizations. They may not have that multiple data set or multiple geological interpretations, and the geologists and GNG, they may have just one interpretation in the end, or one or two, and in that way, that GAN is not ready to. GAN cannot be trained with that small number of training data sets. So that's how the SynGAN, the single image GAN, can be one way, because it has another way to train the features from just one images. So that's why I think this applying or expanding the SynGAN for subsurface modeling problem can be one opportunity for the future work. And yes, this is an ongoing project, and I think some company may already have experience with some implementation of the deep learning. Some company may not. I think one thing that I can say is from BP, when I was working for BP, we had some chance to implement some of the applications, not only for the GAN. The autoencoder is another widely used or popular neural net structures. We've been using the autoencoder or GAN in various tasks, and some of them was really impressing. But not every deep learning is not useful, but some of them is really impressing. So that's the comment that I can make. And yeah, this is really a great question. If it works with a previous method, then why do we still need to? I think, yeah, actually, I do not have a clear answer for the last question. But the industry, what I felt during my PhD, what I felt from communicating with the people from the industry, at some point, they've been experienced the some challenges. For example, the deep water submarine fan. We know that boundary are supposed to be preserved, and there's no straightforward way of preserving that boundaries in our subsurface water. So that's unsolved problem, and people recently start to see that probably this machine learning can one way to tackle that problem. So yeah, I believe most of problem we can do it from our previous method, but the more, if we look into the more details, then there's some opportunity to implement the or apply the machine learning or deep learning in our domain. Thanks, Adi.
Thank you so much, Dr. Joe. Appreciate it. Really appreciate that time. Thank you.
Okay, thank you, Mr. Joe and Adi Junira, Ms. Adi Junira, for the questions. No follow-up question, Mr. Adi?
No, Mas.
All good? Okay. Okay. Okay, thank you very much. And for other participant, you may ask a question. Maybe we can take one or two question from now, since the time has shown 2041 in Indonesia right now, and I'm afraid we don't have very much time more. Yeah, go ahead. Anybody, any participant would love to ask questions about these incredible topics. And for me personally, it's something to be used in the future for machine learning, and I'm also learning coding, and I'm truly impressed. I have to say many times, I'm truly impressed by how you create this generator GAN. And for my personal question, may I ask one? Yeah. About the running time, how long it takes? How long it takes to run from the initial state to your result from right now? And do you use CPU only, or you put a GPU for the running process?
I think people typically says that the GPU training is 20 times faster than CPU training, and thanks to my supervisor during my PhD, he was also very keen to seeing some results from the neural net. So he luckily provided me a really nice GPU in the first year of my PhD. So I was luckily were able to use the GPU as much as I do, or as much as I need. So other training process here, example, I use the GPU, and the training time. For example, this example, this 3D channelized reservoir in a GPU. I do not recall the name for the GPU, but it's not the high-end GPU. It's some typical GPU. It takes about 4 hours, maybe more, 4 hours to 5 hours to complete the training. But what I found is that in the rule-based modeling method, in this example, it took me more time for generating the rule-based model than training the GAN. The training because this 3D is more, it's bigger, and also it's more complicated. So it took me about 1 or 2 days for training the GAN, but generating the training data set takes me about 2 weeks. Because it need a lot of, because and the rule-based modeling method itself is not fast method. It's not like a SGS or SIS. Also, because we need to simulate the sequence of the deposits. So that's why it was really, really expensive. So, and that's why again, maybe having a good enough number of the training data set may be more important than the training itself. And also once we train, making new realizations, it takes less than a second. So we can generate as many samples as we want in a really quick. So, and the training, as long as we have GPU, most of the deep learning algorithm, if it's not too complicated, then they can be trained within a day or 2 days. So, and if I may add one more comment on GPU, actually, when it comes to 3D subsurface model, it easily takes the GPU memory. In the 2D, the GPU memory wasn't a big deal because even if it's a 4K image or the very high resolution images, it just takes the X direction and the Z direction. So that number of the pixels is much less than what we had in this 3D model. In the 3D model, now we have X, Y, and Z. That means the number of the grid in X-axis, Y-axis, and Z-axis. So we need additional dimensions for the memory, and that's why in the up to now, even with the high end like a Tesla 800 or I think there's better GPU memory GPU there, but the I think the maximum GPU memory that are provided in the commercial level is about 80 gigabyte, and that 80 gigabyte is not enough for a real scale subsurface model yet. So that's why in this example, as you might notice it, the size of the subsurface model is really, really small. It's only 64 by 64 by maybe 32 or less. So I think this is ongoing challenging that we may have to get some solution in the end, because some people start to look into how we can save some memories even in the 3D, or some people are still working on what if we just make the 2D images and they stack them over, can then make the 3D models, something like that. So people start to see how we can expand the 3D model in a better way with a given GPU memory, because with a high-end GPU, because a typical GPU may have 8 gigabyte, high-end it only takes 80 gigabyte, but with the 80 gigabyte it's not enough for the full 3D model yet. So that's a one limitation of using the GPU. So
yeah, that's what I thought, that it takes a lot of processing capability to process the code. It seems so complicated. Even 80 gigabytes still not enough. So it means in the future it needs more GPU memory to run for the bigger data, right? For the training.
Right.
Yeah.
It's not accurate, but as a brief broad number, with a 80 GPU, like the best GPU that we have right now, we can probably make the 100 by 100 by 100 size of the subsurface model. But once it's bigger, but typically we may have like a 300 by 300, another 300, right? So still there's more. We need a more GPU memory to make it work. So so that's why we still need to work on this area more sophisticated.
That's one of the limitation, the technology, right?
Yes.
Okay. Maybe other participant who wants to ask the questions. We still have about 10 minutes from now. I think it's already 11 o'clock in Korea, isn't it?
It's 10:50 now. Yeah.
10, yeah. It's 2 hours ahead in Korea. Or participant, you may ask a question in Bahasa, or I will translate in English if you hesitate to write in English. Again, about the TensorFlow, is it is provided with GPU? I mean, the library. Is it does the TensorFlow provide for GPU computations?
I think when you install the GPU, there's a instruction how to couple your GPU with a TensorFlow. So there are two prerequisite program. I do not record right now, but if you search how to install GPU TensorFlow, then from the TensorFlow page, they can provide you how can you do that in more details. How to install GPU TensorFlow. That's
Yeah, TensorFlow seems so powerful.
you may install the CUDAs and some other program as well. But it's not too complicated. Yeah, you can do it for.
Yeah, I'm still learning how to use GPU, and we are in the Ferg right now, trying to use GPU for enhancing the seismic resolutions.
Mhm.
And using basis Pursue inversions method, and we're struggling with the mathematical equation and how to use GPU, and that's still ongoing research in Ferg. Yeah. Okay, seems like there will be no more questions, and I'm afraid we have to come to an end for the event. And thank you very much, Joe Honggeun Sonsenim. Yeah, okay. We call you Sonsenim, right? Is it or Kusunim?
That's a perfect pronunciation. Yeah, actually, yeah, I was surprised. Yeah.
Okay. Okay, thank you very much, Anthony, for the time and for the sharing topic. And for participant, it is recorded and we will upload in YouTube. Is it okay, Sonsonim, to be uploaded, or is it something confidential?
Only if you can delete the Q&A session, because I'm a little bit worried about the comment about the BP, because it may have some, yeah. But other than that, the entire presentation is totally fine.
Got it. Got it. Do. And for the slides for the PowerPoint presentation, can we would you mind to share with us for the participant who wants to read again?
Sure.
Perhaps I will ask Adi Junira, Mr. Adi Junira, as the PIC for the slide. Is it okay?
Oh yeah.
Okay.
I'll get that one. So, thank you so much, Honggeun.
Okay.
Thank you so much. Yeah.
Thank you so much for having me.
Yeah. We have to come to an end. Give applause to everybody. Thank you for the question. Thank you for the sharing. And I know how to end this. Yes. Thank you very much. Thank you very much. Yeah. And see you in the next for a quick discussion next Wednesday. We also have very interesting topics and speakers. And Ferg weekly discussion will be held every Wednesday at 19:30. And that's all. Thank you very much. I don't know how to say it. All right. See you guys. Assalamualaikum warahmatullahi wabarakatuh.
Thank you. Bye, everyone. Thank you.
Bye-bye.